As we delve deeper into the development environment for our course, it's important to note that the primary programming language we'll be using is Python. This course assumes familiarity with Python as a prerequisite, given its widespread adoption and suitability for data-driven projects. Python's extensive libraries and frameworks, particularly those for data analysis and machine learning, make it a valuable tool for modern AI development and research. So, Python, an advanced programming language, was introduced in 1991 by programmer Guido van Rossum. It's an advanced programming language as opposed to a language like C, which are apparently not even taught in schools anymore. So we don't have to go through the struggles as much. Next, it is known for being platform independent, which means that it can run seamlessly on various operating systems, including Linux, Windows, and Mac OS. Unlike languages that require compilation, such as C, Python is interpreted. This means that Python code does not need to be compiled before it is executed. You can simply write your code and run it directly, which streamlines the development process by eliminating the build process. This immediate execution feature of Python makes it exceptionally suitable for rapid prototyping and iterative development, where developers can quickly test and modify their code on the fly. Being interpreted also allows Python to be highly flexible in testing and debugging scenarios. Developers can execute sections of code or changes immediately without waiting for the entire application to compile. Furthermore, Python is both object-oriented and dynamically typed. Being object-oriented allows for structuring software in a modular and reusable way, using objects and classes. The dynamically typed nature of Python means that you do not need to explicitly declare variable data types. The language automatically infers them, which can speed up coding and reduce the boilerplate code seen in more statically typed languages like Java or C++. So, we briefly talked about what Python is as a programming language, but Python's simplicity and readability make it an ideal programming language for beginners, including those who haven't specialized in computer science. Its straightforward syntax closely mimics natural language, which reduces the learning curve and helps new programmers to pick up concepts quickly. This simplicity is crucial for individuals in fields such as biology, economics, or psychology, where programming is a useful tool but not the primary focus of the study. Python syntax allows these users to write scripts that perform complex tasks, from data analysis to automating repetitive tasks, without getting bogged down in the intricacies of the verbose programming languages. Moreover, Python's widespread adoption isn't solely because it's easy to learn. Other languages like Ruby are also known for their ease of use and beginner-friendly syntax. Ruby, for instance, is another high-level language celebrated for its elegant syntax that many find intuitive. However, Python distinguishes itself through its extensive use in scientific computing, data science, and machine learning. The vast ecosystem of libraries and frameworks, such as NumPy for numerical computations, Pandas for data manipulation, and TensorFlow and PyTorch for machine learning, extends Python's capabilities far beyond basic programming tasks. This extensive support makes Python particularly valuable to researchers and developers who are more focused on pragmatic application. Next, the strong community of Python significantly enhances its appeal, especially for beginners and those from non-CX backgrounds. The vast number of Python users contributes to a very active online community on platforms like Stack Overflow and GitHub. This community is incredibly resourceful for troubleshooting and sharing a wide range of coding issues and solutions. For instance, if you encounter a problem or need to understand a particular piece of code, it's highly likely that someone has already asked a similar question or shared a relevant solution. Moreover, the integration of Python into tools like ChatGPT has broadened its utility. Since ChatGPT has been trained on diverse datasets that include code from Stack Overflow and other coding forums, it can assist with Python coding queries effectively. This makes Python not just a language for coding, but part of a larger ecosystem that supports learning and problem solving in real time. Python's simplicity also extends to areas like statistical analysis, where it competes with more specialized software like R and SAS. Libraries such as SciPy and stats models provides powerful tools for statistical analysis, which are accessible directly within the Python environment, making it easier to integrate and manipulate data without switching between tools. The presence of Python on platforms like Stack Overflow, where millions of developers share knowledge and solve programming issues, creates a rich repository of real-world coding examples and solutions. This collective knowledge is leveraged by AI models like ChatGPT and Bard, which can then provide informed, contextually relevant advice on Python programming. As a result, Python users benefit immensely from this synergy, accessing both human and AI-driven insights to enhance their coding practices. Then, the last part is the large set of libraries available in Python. These libraries are essential collections of pre-written code that developers can import and use in their own projects, significantly reducing the need to reinvent the wheel. By leveraging these libraries, you can incorporate complex functionalities into your applications without having to code them from scratch. This aspect of Python is a tremendous boon for efficiency and innovation. For instance, in the realm of AI and machine learning, libraries like PyTorch and TensorFlow offer ready-made tools that simplify building and training neural networks. These libraries provide a high-level abstraction over intricate algorithms and mathematical operations, making it easier for developers to implement state-of-the-art AI models. PyTorch is particularly appreciated for its dynamic computational graph that allows for modifications to the network architecture on the fly during execution, which is a significant advantage during the experimental stage of model deployment. TensorFlow, on the other hand, excels with its robust, scalable, and production-ready environment that supports both research prototyping and deploying models in production settings. Thanks to the robust ecosystem of Python libraries, there's no need to code from scratch, especially when it comes to complex tasks like building neural networks. This capability accelerates the development process by providing pre-built modules and functions that abstract much of the underlying complexity. As we progress through the lectures, we'll go through the different libraries used in different parts of the pipeline. Now that we've looked at Python, let's dive into an essential component of development preparation, the programming tool known as an IDE, or Integrated Development Environment. IDEs streamline the coding process by integrating all the necessary tools into one interface, enhancing productivity and simplifying the software development lifecycle. They offer a user-friendly way to write, test, and debug code without switching between different applications and tools. An IDE is defined as a software for building applications that combines common development tools into a single graphical user interface. This is similar to how Microsoft Word functions for document creation. Just as Word provides tools for writing and editing documents, an IDE offers integrated tools tailored for software development. One major advantage of using an IDE over a simple text editor like a Windows terminal or Mac OS terminal is its graphical user interface. This interface significantly enhances usability and efficiency. For instance, by clicking on a class we've imported from a library within an IDE, we can immediately see what functions and attributes are available to us. This direct interaction facilitates easier and more intuitive development. IDEs are comprehensive tools that support all parts of the development process, including features like spell check and indentation checks, features that anyone who has coded using basic text editors like Vim or Emacs will greatly appreciate for their ability to catch simple errors. Furthermore, many IDEs come equipped with integrated version control systems, which allows developers to track and revert changes easily. This integration is vital for maintaining a clear history of modifications and collaborating effectively in team settings. Additionally, IDEs often include intelligent code completion or code suggestion features, which helps speed up the development process. To discuss the components of an IDE, first is a source code editor. This is a core component where you write and edit your code. It is designed to help developers manage complex code bases more easily. Next is local build automation. While Python is an interpreted language and does not require a build process, this feature is crucial for working with compiled languages or libraries that require building like C and Rust. Next is a debugger. This feature in an IDE is similar to the spell check function in a word processor. It automatically checks your code as you write, providing immediate feedback on errors, and not only tells you that there is an error, but often can pinpoint its origin. This feature is invaluable because it saves time and frustration compared to debugging in a less integrated environment like a terminal. Various IDEs are available to suit different programming needs. JetBrains, for example, offers PyCharm for Python developers and IntelliJ for Java developers. Microsoft Visual Studio Code is another popular choice, especially among those who appreciate its versatility and no-cost offering. However, if you're a student, you can use PyCharm for free. Each IDE tends to have a unique set of features that may be more or less suited to the specific types of projects or developer preferences. For example, Eclipse and NetBeans are favored in the Java community for their extensive plugins and support for application development, while web designers might lean towards lighter, more flexible environments like Sublime Text or Atom that offer fast performance and a clean workspace. Unlike older IDEs like Eclipse, newer IDEs like Visual Studio Code have gained popularity due to their speed, streamlined user interface, and powerful features such as direct integration with Git repositories, which simplify version control operations directly from the IDE. This versatility makes Visual Studio Code a compelling option for developers working across different languages and frameworks. Choosing the right IDE often depends on the specific needs of the project and personal workflow preferences of the developer. For me, I use a text editor and also an IDE depending on the task that I'm working on. However, for collaborative projects or distributed teams, tools like Google Colab are often used because of their support for collaborative working environments. However, for personal development, many developers find that Visual Studio Code meets all their needs efficiently. By understanding and utilizing the right IDE, developers can enhance their productivity and focus more on solving complex problems rather than getting bogged down by the mechanics of code editing and debugging. When you join a firm as either a data scientist or a software engineer, you might have to switch around IDEs, so it's good to know which ones exist. Now, we'll explore a key tool in machine learning and data science development, Anaconda. I've considered various points in the curriculum to introduce this, given its importance. Anaconda is a robust open source platform that simplifies Python and R, data science and machine learning on a single machine. It's particularly well suited for individual developers looking to create a manageable environment for these tasks. Its comprehensive suite of over 1,500 plus open source packages make it an invaluable resource for scientists, engineers, and data analysts aiming to simplify package management and deployment. One of Anaconda's core strengths is its ability to handle virtual environment configuration and library management. This is crucial because data science and deep learning require very specialized libraries like PyTorch and TensorFlow for deep learning, scikit-learn for machine learning, and libraries like scikit-image and OpenCV for image processing. Anaconda streamlines the management of these libraries, ensuring that dependencies are resolved without conflicts that can lead to crashes. By efficiently managing these aspects, Anaconda allows developers to focus more on innovation and less on maintenance. Additionally, Anaconda comes with tools like Jupyter Lab and Jupyter Notebook and Spider, IDEs that are tailor-made for data science workflows. These tools support interactive coding, data visualization, and report generation, which are integral to data science. The advantage of using Anaconda is its open source nature, aligning well with the community-driven nature of Python ecosystem. Anaconda is also specialized for data science, supporting both Python and R. two of the most popular languages in data analytics. Besides providing essential IDEs like JupyterLab and Spider, its real strength lies in convenient library management and virtual environment configuration. These environments are crucial for isolating projects to maintain dependencies specific to each project. This means if you update a library for one project, it won't disrupt another project that might rely on an older version of that library. This isolation is key in an environment where different projects may require different versions of the same library to function correctly, ensuring that updates or changes in one workspace do not cause failures or conflicts in another. Additionally, this approach facilitates easier rollback to previous versions if an update proves unstable or incompatible with certain aspects of a project, thereby enhancing the overall robustness of development workflows. Moreover, Anaconda's ability to manage different environments efficiently allows data scientists and developers to experiment with various libraries and versions without risking the stability of their main development environment. This flexibility is particularly beneficial for testing new tools and algorithms that are continuously emerging in the fast-paced fields of machine learning and data science. By providing a safe sandbox for experimentation, Anaconda helps foster innovation while minimizing the risk of disrupting ongoing projects. So, now that we've explored the numerous advantages of Anaconda in streamlining and safeguarding the development process, let's shift our focus to some of the potential drawbacks and limitations of using this platform. The trade-offs include Anaconda's large size, which can be cumbersome, and the update delay due to its focus on library stability over having the latest versions immediately. For instance, if a new version of a library introduces a better neural network model, projects confined to older versions may struggle to integrate these changes without extensive reconfiguration. This scenario can impact data scientists and developers working in rapidly evolving fields where staying current with the latest advancements is crucial. Being unable to quickly adopt new features or improvements can hinder the competitiveness and effectiveness of their work. Furthermore, the heavy footprint of Anaconda might lead to longer setup times. In our upcoming discussion, we'll touch on how modern tools like Docker can help manage even hardware configurations, though it's a more complex system not typically necessary for individual projects on personal machines. Docker provides a layer of abstraction that can be crucial for larger, more complex development scenarios, but might be overkill for smaller projects. We'll discuss further in the upcoming slides, but to give a brief overview, Docker's primary utility lies in its containerization technology, which allows developers to package their software with all of its dependencies into a standardized unit for software development. This ensures that the software runs reliably regardless of differences in OS distributions and underlying infrastructure. Now, let's delve into the Python libraries that are managed by Conda. These libraries are essential tools that enhance Python's functionality across various domains, from handling complex numerical calculations to processing images and beyond. Conda's comprehensive library management system simplifies access to a wide range of tools that are fundamental to modern scientific computing and data analysis. So far, in terms of libraries, we've talked about libraries like PyTorch and TensorFlow, which are fundamental for deep learning. Additionally, the OS library manages system-related work, which is particularly crucial in Anaconda as it helps set and manage system paths. This functionality allows us to create, change, and delete directories, streamlining file management across different operating systems. NumPy used for efficient mathematical operations. Whether you're calculating square roots, squares, factorials, or generating random numbers, NumPy provides these tools outside of the box, saving you from having to implement these functions from scratch. NumPy is also pivotal for more complex numerical computations. It supports large, multidimensional arrays and matrices, along with a vast collection of high-level mathematical functions to operate on these arrays. The performance optimizations in NumPy make it highly efficient for numerical computations, which is why it is the foundation for many other scientific computing libraries. So, NumPy configures the hardware to run a little more efficiently. Matplotlib is another critical library used extensively for visualizing data. If you have a background in engineering, you might be familiar with MATLAB. Matplotlib brings many of MATLAB's functionalities into Python, enabling everything from simple 2D graphs to more complex 3D visualizations. Beyond basic charts and histograms, Matplotlib allows for the customization of every element of a plot, including size, color, and type, making it possible to tailor the presentation precisely to specific analytical needs. It supports a wide array of plot types, such as scatter plots, bar charts, contour plots, and even non-Cartesian coordinate systems. For video and image processing, OpenCV and scikit-image are the go-to libraries. OpenCV focuses on real-time image processing, while scikit-image provides tools for image manipulation, both being essential depending on the project's needs. But basically, they offer similar set of functionalities, so this one is by preference. When it comes to data management and analysis, Pandas is the library of choice. It allows data to be organized in a tabular format similar to Excel, making it intuitive for managing data with rows and columns. It also offers functionalities to export data to Excel files, enhancing its utility in data analysis tasks. Furthermore, Pandas provides powerful data manipulation capabilities such as merging, reshaping, selecting, as well as handling of missing data. Next is Simple ITK, specialized for medical image processing. This library is an example of Python libraries that were tailored for specific fields. For instance, during my astrophysics days, I frequently use AstroPy, a library optimized for astronomical data analysis, similar to how Simple ITK is used in medical fields. For example, Simple ITK, with this comprehensive suite of tools designed for image registration, segmentation, and advanced image analysis. Next is scikit-learn. Scikit-learn is broadly used for machine learning, offering tools like Gaussian mixture model and many other algorithms that facilitate both simple and complex data analysis and modeling tasks. Lastly, TensorFlow and PyTorch are not just general deep learning libraries, but are foundational in advancing the cutting edge of AI research. Next, let's discuss Docker, a crucial concept for those looking to deepen their understanding of software development environments. While Docker might seem advanced for beginners, it's an essential technology for developers, especially when deploying models or collaborating on large projects. In this lecture, we'll stick to using Colab for simplicity, but understanding Docker is highly beneficial for any serious developer. Docker was developed to address the need for consistency across multiple development, testing, and production environments. It simplifies the process of pushing changes or new versions without the fear of creating discrepancies between environments. So now, to go into the definition of Docker, Docker is a software that provides ability to isolate data or programs. So, you may ask yourself, why is this isolation important? This isolation is crucial because it ensures that applications run the same way on every developer's machine as they do in production, eliminating the works on my machine syndrome that can lead to significant delays and frustrations in development cycles. Traditional development environments often face compatibility issues because each developer's machine can have different configurations. For instance, if the development environment relies on specific Python libraries or driver versions, problems arise when these dependencies vary from one PC or server to another. This discrepancy can lead to significant issues, such as a driver version mismatch when a firm upgrades its GPU, potentially causing previously functional code to fail. For example, if a software was originally developed using NVIDIA's GTX 100 GPU drivers and the company upgrades to a newer GTX 200 series, the new drivers may not support certain functionalities used in software, leading to unexpected breakdowns or performance issues. Additionally, significant changes in software versions, like moving from Python 2 to Python 3, or major updates in libraries like PyTorch and TensorFlow can alter syntax and functionality dramatically. Even in minor updates, such as from 1.1.2 to 1.1.3, might post big changes, but jumping from version 1 to 2 can require extensive code modifications. For instance, the transition from Python 2 to Python 3 involved changes such as the print function syntax and handling of integer division, which significantly affected legacy code and required substantial updates. Another example is TensorFlow 1.x to TensorFlow 2.x, which introduced a shift to eager execution by default and a more intuitive and simplified API, requiring developers to refactor their existing TensorFlow 1.x code to accommodate these new paradigms. Therefore, it becomes essential to customize software to match the user's environment, not just the developers. This customization can be particularly challenging when developers use different hardware, such as various GPU models or different operating systems, which may handle pathing differently. For example, Windows uses backslashes, while Linux and Mac OS use forward slashes. Another common issue is the different handling of line endings, where Windows uses carriage return and line feed as a line ending, whereas Linux and Mac OS typically use just the line feed. This can lead to significant problems in text processing and version control systems, where line ending discrepancies can corrupt files or disrupt application functionality. Additionally, window environment variables and system settings that differ from one OS to another can lead to unexpected behavior or errors in applications that are not thoroughly tested across platforms. So, what solution does Docker provide? Docker enables the creation of isolated environments, known as containers, which can run consistently across any hardware configuration. This feature allows multiple developers to work on a single server, but maintain their own independent development environments tailored to their specific project needs. This isolation is achieved through the use of Docker containers, which encapsulate and isolate software, libraries, and their dependencies. Containers are lightweight, which ensures that resources are and they can be created, started, stopped, moved, and destroyed with ease, without affecting the underlying server or other containers running on the same machine. Looking at Docker's architecture, the client interacts with the Docker host via daemon, which manages Docker images pulled from containers. These images act as templates that provide all the necessary components of a development environment. To understand Docker's core components, consider images and containers. An image serves as a blueprint for creating a development environment, specifying which versions of Python, PyTorch, CUDA, and system drivers to use. Containers are the instances created from these images, essentially functioning as encapsulated, portable environments where developers can work without affecting their underlying system. Once a container is launched from an image, it operates independently of its host system, allowing developers to run applications in a controlled and consistent environment, regardless of where the container itself is deployed. This independence is crucial for developing, testing, and deploying applications that need to perform reliably across different computing environments. By distributing software as Docker images, developers ensure that anyone can replicate their development environment exactly, sidestepping the typical issues related to system differences. This capability allows for the seamless execution of software, agnostic of the machine's local configuration. Additionally, this approach significantly simplifies the onboarding process for new team members and reduce setup errors, as developers can get started with pre-configured environments with minimal setup time. Before Docker, developers had to account for various potential configurations of user machines, which could be a complex and error-prone process. But with Docker, developers can simply upload an image of their work to a registry from which others can easily download and run it in the exact same environment, thereby streamlining collaboration and this process also enables a seamless update mechanism, where improvements or bug fixes are integrated into the Docker image and made instantly available to all users. In summary, think of Docker images and containers as a way for developers to package and distribute their entire development environment. Users can then utilize these packages without having to set up the environment themselves, allowing them to operate within a fully functional, isolated workspace right out of the box. This concept, while advanced, is crucial for those looking to professionalize their development practices or collaborate effectively in diverse teams. If you're new to Docker, these concepts might seem abstract and a bit confusing at first. The best way to grasp how Docker functions is by hands-on interaction. I recommend following a step-by-step tutorial to set up and deploy your own Docker containers and images. This practical approach will help you understand the setup, management, and deployment process that Docker simplifies. Docker is incredibly versatile and can be used across various fields, including deep learning, web management, app development, and even game development to deploy finished products or models efficiently. Whether you're pushing a complex AI model into production or rolling out updates to a multiplayer game server, Docker offers the tools necessary for seamless development. Furthermore, if you plan to work in a tech company, understanding Docker is essential, as it's often integral to modern development pipelines. It enables teams to manage and deploy applications in a unified environment, ensuring consistency and collaboration among developers, regardless of their physical location.